All right, so now that I've introduced what is an ordinary differential equation, we're going to now talk about what does a solution look like to an ordinary differential equation. But we're going to start by actually saying, let's remember what solutions to equations even mean, right? So you may have seen this many years ago in an algebra class, right? Is x equals 5 a solution to the equation x squared minus 25 equals 0? And you would say yes. It is a solution, right? You plug in the 5, you get 25 minus 25, you see, oh, that does equal 0. It's a solution because it makes the equation true, right? And it's not the only solution, right? We could also look at, x equals negative 5. That's also a solution. You could have equations like x minus 5 squared equals x squared minus 10x plus 25, and this equation has infinitely many solutions, right? A solution is just something that makes the equation true. So it's going to be the exact same thing for an ordinary differential solution. So question is P equaling to P naught e to the kt a solution to the differential equation dp dt equals kp. Remember when I said you needed calculus? Well, this is why. How can we even check whether something's a solution? We have a derivative right here. We're going to have to find out, right? So we'll say, okay, well, what's the left-hand side of this equation, right? What's the left-hand side? Well, that's the derivative of p with respect to t. We have to take the derivative of this. Remember that these two guys are constants. So we're just taking the derivative of an exponential function, and we're going to need the chain rule. Derivative of an exponential function is itself. Use the chain rule to multiply by the derivative of the inside. Again, refresh that chain rule. Practice working with constants and parameters because we are going to be doing a ton of that this quarter. Okay, so that's the left-hand side. We could simplify that a little bit, right? That's just k times p naught e to the kt. Well, if it's a solution, that should equal the other side. So the right-hand side is just k times p. Well, what was p? P was p naught e to the kt, and what you're going to see, right? Oh, let's use a different color. The left-hand side and the right-hand side are exactly the same. Yes, this is a solution. I didn't show you where this came from. We'll do that later on in chapter 1. This is an analytic solution, by the way. That's going to be an important type of solution. Analytic solutions to differential equations. Those are essentially going to be solving by hand. Is usually how we're going to do them. It's a closed formula. Right? Your solution is a formula. It's a formula, often by hand. Analytic solutions are very nice because then we know everything that's consistent with the model. We still have a problem of the model doesn't necessarily the model still doesn't necessarily reflect reality, right? When we talk about population growth, this is our model and we can solve this model exactly. But this is not a perfect model of population growth in the first place, right? Things don't grow without bounds. So that's one of the interesting things about modeling is that even if we can solve a model, the model still doesn't perfectly relate to real life. And so what we do is we make more and more complicated models to make better models, which are harder to solve, but they more accurately reflect reality. And sometimes we may intentionally choose a simpler model to just make our lives easier, knowing that we don't need that level of precision. We don't need to reflect reality that well sometimes. Okay, because some models can really take a long process with numerical methods. This is an analytical method to get analytic solutions. We'll talk more about numerical methods later, but that's using a computer to approximate. Okay, so it really just depends on what you're doing and what the situation is. So yes, here are some solutions. And the reason why I'm saying some solutions is because this is actually infinitely many solutions. It really just depends on what P naught looks like. So this is what's known as the general solution to the initial value problem. Okay, and maybe we'll just do a bunch of definitions in yellow. All right, this is the general solution to the initial value problem. General solution, because it's really infinitely many solutions. I haven't told you what this P naught is yet. No matter what P naught is, no matter what our starting population is, this is going to be the solution for all of them. This P naught really is, by the way, where does that come from? It comes from when you're integrating and you have that plus C. Remember when we say find an antiderivative, we have infinitely many antiderivatives. Just like, oh yeah, they can all differ by a constant. Well, this is really the same thing, and we'll show why in a future section, but essentially the plus C turns into a P naught in this solution. And again, if you're really curious to find out why, we got it in a future video coming up for you. All right, so that's pretty interesting. So this is a general solution. And of course, and it depends on the initial condition, which we introduced over here. This over here was the initial condition, the thing that makes it an IVP, an initial value problem. I know so many terms, but don't worry. We'll be using these terms more. They'll become second nature pretty soon. It's not something that is, we're not working with really precise definitions at the moment. So it's a general solution. A particular solution would be if I told you what P naught was, right? We said the general solution was that P of t was some initial value times e to the kt, like so. Oops, sorry, circling the wrong part, right? That was our general solution. General solution was this. It's a solution, specifically it's a general solution, right? So that was our general solution. But if I told you our initial condition, and let's say I told you that we started with 100 moose. Well, now all of a sudden, you know that P naught is 100. And now we know that our solution looks like 100 e to the kt, right? This is what's known as a particular solution. Because now that initial condition is more firm, right? We know exactly the situation that we're talking about. We know all population growth with this model will look like this. This is the general solution to that initial value problem. That's what the particular solution's going to look like. Okay, so there's really a lot going on here, a lot of verbs, and I don't want you to get too overwhelmed by the technical things, by the technical definitions. So again, we know that the solution looks like this. It's exponential growth. We know what exponential growth looks like. And now what's interesting is that with general solutions, right, there's not just one solution. There's one particular solution. And that particular solution, right, was when we started with 100 moose. And we could zoom out to make this look better, but you know, we have another particular solution for if we started out with 2 moose. I like moose. I don't like saying the plural of moose is moose, but that is correct. And so, of course, it turns out that there are infinitely many particular solutions. Or, like, depending on the situation, really what we should say is that there are infinitely, like, the general solution encompasses infinitely many solutions. These are all solutions. Every single graph that you're seeing is a solution to the initial value problem, depending on what that initial condition is. Okay? So what we do a lot of times is we might say, what does a general solution look like? We'll graph it. We'll show some of them. So we'll say, okay, general solution is really going to look like this. There will be one solution that might look like this. There will be another solution that looks like this. There will be another solution that looks like this. If we did allow for negative values, we could have solutions that look like this or look like this. There's so many solutions. And so get used to seeing some graphs like this. When we're dealing with general solutions, there's going to be infinitely many. And here they all behave pretty similarly. But it turns out that there's another solution that looks a bit funny. This is also a solution to the differential equation, depending on what that initial value is. And this one is called something special. This one down here is called an equilibrium solution. And specifically, it's just when the derivative equals 0. Equilibrium is balance, right? It's some level of stability. Specifically, when we talk about equilibrium solutions, we'll talk about when the derivative is constant, when things are not changing. And this is specifically for our first order differential equations that work like this. And we can find this equilibrium solution with this condition. So when is dp dt equal 0? Well, what was dp dt? dp dt was just k times p. So that's going to be true when k times p equals 0. And we just solved this equation. K is a constant. We can divide both sides by a constant. And that's just when the population is 0. And again, when we think about population growth, of course that makes sense. If we have no moose, then they will not be able to breed and grow. They will not be able to die. If we have no moose, we will always have no moose, unless something new comes into the system. All right, so that is our equilibrium solution. It's just, well, if the population is 0, it will always be 0. All right, so that's most of the things I wanted to talk about in this video. A reminder that this is all like an analytical solution. We get an exact function that models and solves the differential equation. A lot of times we'll do that by hand. This is to be contrasted with qualitative analysis, which we're going to do in the next video by looking at some graphs, and we'll also do later on with the introduction of slope fields in a future section in this chapter. Okay, so this is one type of solution. This is analytic solutions. We talked about general solutions and particular solutions. Those are all all part of analytically solving a differential equation. All right, until next time, qualitative analysis.